So a couple things I noticed on some of the most recent homework assignments I just want to point out to everybody. There were two things specifically that I have seen from more than a few of you. When you're solving a quadratic equation, if you factor, which is totally fine, we can't stop at the factoring. So if someone says solve x squared minus 3x minus 4 equal to 0, and you factor it as x minus 4 times x plus 1 equal to 0, that's not the end of the problem. You still have to say what the solutions are. I know you know what they are, but if you don't write down x equal to 4 or x equal to -1, the person grading your work isn't going to know that you know what the answer is. So make sure that if you're solving an equation, you actually write the values that x is equal to. Whereas if someone just says factor, they're not asking you to find x values, they're just asking you to factor. So there's a difference, right? Solving an equation, you should get x equal to something or whatever your variable is. Factoring something, they're just asking you to rewrite it. Speaking of factoring, I saw some people when they factor something with a non-1 coefficient, so like a 2 or a 3 or something else out here. I know like we do the thing where we're like, okay, a times c is 2 times -4, which is -8. And then we're looking for numbers that multiply to -8 and add up to 7. And those numbers in this particular problem are +8 and -1. If they multiply to -8, they add up to +7. But the thing is, those aren't the numbers. Usually they're not. Occasionally it works out that they are, but these are not the numbers that are going to end up here when we factor it. Because if you do x plus 8 times x minus 1, you're going to get x squared plus 7x minus 8. The middle term will work out, but the other two parts won't. So when you're doing it this way, specifically when you have something here that's not equal to 1, if you're going to do this thing where you look for two numbers that multiply to a times c and add it to b, then after you find those two numbers, in this case 8 and -1, you have to rewrite the middle term as a sum of those two numbers. So in this case, we're writing 7x as 8x minus 1x or plus -1x. And then you're going to factor by grouping. So from the first term, from 2x squared plus 8x, you can factor out a 2x and you're left with an x plus 4. And from the -1x minus 4, you can factor out a -1 and have a -1 times x plus 4. And then you can factor out the x plus 4 from each of these and get x plus 4 times 2x minus 1. That's how this one should factor, right? So, and again, if you think you factored it right or wrong, right? If you're not sure if you factored it right, you can always do a quick check. If you multiply the first two things together, the x things, they should equal the x thing there. X times x is x squared. It's not 2x squared. And also the last two things multiplied together should equal that. 8 times -1 does not equal -4. Whereas with this one, it totally works. X times 2x is 2x squared. 4 times -1 is -4. So that's why you can check if you're not sure if you factored it right or not. But just be careful. I know it's really easy to be like, oh yeah, 8 and -1, it's x plus 8 times x. No, it's not always, it doesn't always work like that. Specifically, it doesn't it doesn't always work like that when you have a non-1 leading coefficient. If it's 1, it totally works. If it's not 1, it usually doesn't. So just a couple things I noticed while grading your homework, which I have not finished doing, but I will finish doing. Let's go ahead and get to the meat of today's class, which is talking about graphing other polynomials. And we're going to start by graphing a couple parabolas. So we're going to compare the graphs of y equals x squared minus 4 and y equals x squared minus 4x plus 4. And I picked these two specifically because they kind of have some very interesting features. I factored them just to kind of show the factors. So x squared minus 4 factors as x minus 2 times x plus 2. You can also think of it as the usual pairing graph shifted down 4. So if I was graphing y equals x squared, the vertex would be at the origin. I'm graphing y equals x squared minus 4, it's going to shift it down 4 so that the vertex and the y-intercept are both at the point 0, -4. And also, we can see from the way this factors that the x-intercepts would be +2 and -2. Yeah, so that's that one. And then, and I could write down all the things. The vertex is 0, -4. The Y-intercept is also 0, -4. And the X-intercepts are 2, 0, and -2, 0. I should mention, if you don't have a middle term, right, if you don't have a b, or if b is equal to 0, right, if there's no x term, you're just shifting the graph up or down, which means the vertex is going to be the same as the Y-intercept, because your highest or lowest point will just be where the vertex shifted to, which is where the Y-intercept ends up being. That's only if you shift it just up or just down. On the other hand, we have this, y = x squared minus 4x plus 4, which we can also factor. It factors as x minus 2 times x minus 2, which we could then simplify as y = x minus 2 squared. What I want to mention for this one is it is just taking your original parent parabola with the vertex at the origin and shifting it 2 to the right. So I'm going to try and draw it here. Kind of, yeah, I've got enough room. So for this one, the vertex would be at the point 2, 0. Do I have enough room? Maybe. So the vertex would be at the point 2, 0. You can either justify it to yourself by saying, well, I'm taking my old graph and I'm shifting everything 2 to the right. So the vertex that would have been at the origin is now at the point 2, 0. Or you can find it the other way, right? Or you can see that it's at the completed square form, and the x coordinate is 2 and the y coordinate is 0. Or you can do negative b over 2a. -4 over 2 times 1 is positive 2. And if x is 2, y is 0. And then the y-intercept is going to be 4. If x is 0, y is 4. And then we can see that the x-intercepts are also both 2 because we factored it, and the only way this is equal to 0 is x is 2. And I'm going to try and draw it. It's probably not going to look excellent. Okay, I've drawn better. Okay. I don't really care so much about how these graphs look. But what I really, really want you to notice is that this graph has 2 x-intercepts, and at each of these x-intercepts, the graph crosses the x-axis as we go from left to right. So if you look at this graph from left to right, I'm above the x-axis, and then I hit the x-intercept, and then I cross being below the x-axis. And so I keep going from left to right, then I'm below, and as I get to this x-axis, this x-intercept, I hit the x-intercept, and I cross the x-axis back to being above. So I would say left of this x-intercept, the graph is positive. Between this x-intercept and this x-intercept, the graph is negative. After this x-intercept, the graph is positive. On the other hand, for this x-intercept here, we have different behavior. We come down, we get close to this x-intercept, and instead of crossing the x-axis and going negative, we bounce off the x-axis and stay positive. That's really what I want you to see here, is that for these intercepts, we cross. For this intercept, we bounce. And there's a very kind of, what's the word I'm looking for? There's a very natural way of deciding what does what. It's based on whether or not the power of the factor is odd or even. So these factors both have odd powers. Right? They're both raised to the first power. And at these odd powers, the x-intercept that comes from that factor with an odd power, we're going to cross. The graph is going to cross at that x-intercept. Whereas with this even power, at the x-intercept, which is positive 2, if your power is even, we're going to bounce. Another way I like to say that, I'm going to write something down to say it, is that for odd powers of x-intercepts, the sign of the function changes. It goes from positive to negative or negative to positive as you cross. Whereas for x-intercepts with even powers, the sign of the function doesn't change. We were positive on the left side of this x-intercept, and we stayed positive on the right side of this x-intercept. Okay. let's write down a few things here. Okay. So let me see what I want right here. Yeah, there's a lot of words. So here's what I really want to write. For X, so for X intercepts that come from factors raised to even powers, the graph of the function will bounce off the x-axis. Or as I also like to say, it'll stay on the same side of the x-axis that it was already on. If it was above, it'll stay above. If it was below, it will stay below. On the other hand, and write the same words, just change a couple of them. For x-intercepts that come from factors raised to odd powers, the graph of the function will we either say cross or go through the x-axis. Typically, we think of going from left to right, but it doesn't actually matter. You can think of it from right to left as well. You should always think of it as either bouncing for even powers or crossing for odd powers. And that is, I should point out, the power of a factor, the power of a factor is called its multiplicity. So in the previous example, or examples, I would say that the factor x minus 2 has a multiplicity of 1. I would also say that as the x-intercept x equal to positive 2 has a multiplicity of 1. I would also say that x equal to negative 2, the x-intercept has a multiplicity of 1. And over here, I would say that the x-intercept of positive 2 has a multiplicity of 2. So it's really important that when you have a factor that's repeated, like x minus 2 times x minus 2, you don't say to yourself, oh, I have 2 intercepts, 2 and 2, and they both have a multiplicity of 1. No, we have to put it together. So we can say, oh, I really have x minus 2 squared. And so the x-intercept of positive 2 has a multiplicity that is also 2. So that's kind of the idea. Let's do some examples. The reason we're talking about this is it's going to help us graph polynomials that have higher degrees than just quadratic. So let's talk about, say, this example. Let's look at y equal to x cubed minus 3x squared. And so if I'm going to try and graph this thing, let's see what I want to say here. Yeah. Really what I want to do is find the intercepts. So I should point out anything that's higher degree than quadratic, you're not going to have like all the stuff, right? We're not going to have a vertex. That's kind of the other thing. We're not going to have a vertex. Right? If it's not quadratic, you don't have a vertex. If it's a higher degree polynomial, you don't have a vertex. So this is a third degree polynomial. So the degree is 3. And in general, the degree of the polynomial is just the highest power of x that happens to be there. And if I want to find the intercepts, well, let's find the intercepts. So to find the y-intercept, we're going to set x equal to 0, as we always set x equal to 0 to find the y-intercept. And to find the y value, we're going to get y equal to 0 cubed minus 3 times 0. Yes, we know it's going to be 0. 0 minus 0 is 0. Great, so the origin is my y-intercept. It's also an x-intercept, right? Because the origin is both an x and a y-intercept. So we got the origin. So when I start finding my x-intercepts, I already know what one of them is going to be. I know one of them is going to be 0. But typically to find the x-intercepts, we're going to set y equal to 0. So I'm going to get 0 equal to x cubed minus 3x squared. And the idea is that whenever you're finding the x-intercepts, typically you want to find them by factoring the thing if you can. And this definitely factors. We can factor out an x squared. And if we factor out an x squared, we're left with an x minus 3. Now you don't have to write this, but I'm going to point out, we could write this a little bit more explicitly. We could write this as x minus 0 squared times x minus 3 to the first, if we really, really wanted to. We don't need to do that, but I want to just make it clear what we have. So my x-intercepts are x equal to 0 and x equal to 3. Can anybody tell me what is the multiplicity of the x-intercept x equal to 3? You can write it in the chat. You can show me your fingers, just not that one. Right, exactly. The multiplicity is 1 because 3 came from the factor that was raised to the first power. Right, so again, right, 3 did come from this factor. We're getting x equal to 3 by setting x minus 3 equal to 0. And in a similar way, 0 came from this factor, x squared, or if you prefer, x minus 0 squared. But we usually don't write it this way. We're usually thinking of, oh, we're just getting it from x squared equal to 0. And then you could square root both sides, or really just set the inside equal to 0. So x equal to 3 has a multiplicity of 1, like we said. And x equal to 0, well, 0 came from this factor, either way you want to write it. And that factor has a multiplicity of 2. So we know when we graph this thing that at the x-intercept of 0, 0, our graph is going to bounce off the x-axis. And our x-intercept of 3, 0, our graph is going to cross through the x-axis. So let's, we usually do one more thing. So there's one more thing we sometimes do. I don't particularly always care to do it, but some people do like to make a sine chart. So I'm going to make a sine chart. And the only numbers you want to put on your sine chart, if you're talking about a polynomial, is the numbers that are x-intercepts. Or in other words, the numbers where the function is equal to 0. So on my sine chart, all I really want is x equal to 3 and x equal to 0. And now I'm just going to test a point in each of the 3 regions or 3 intervals to see if the graph is positive or negative. Now here's the thing. I only have to test one point in each of these because I know once I test a point, well, in fact, let's just test a point and see. So let's say we check like x equal to 5. Here's the thing. I don't want to calculate 5 cubed minus 3 times 5 squared. I don't really care what the number is. I just care if it's positive or negative. And it's much easier to see if it's positive or negative by looking at the factored form. If I plug in 5 to that, I can see that I'm going to get 5 squared times 5 minus 3, which is a positive times a positive, which is positive. And it doesn't matter if I pick 5 or 5 million. Anything that's bigger than 3, x minus 3 will be positive, and x squared will be positive. But then if we pick something between 0 and 3, well, now here's the thing. We could pick another number. We could pick x equal to 1. Pick x equal to 1. 1 squared is positive. 1 minus 3 is negative. A positive times a negative is negative. Or we could use our knowledge that 3 has a multiplicity of 1. So the graph is going to end up crossing the x-axis, which means the sign is going to change from being above positive to being below. And then if you pick something less than 0, like -5, -5 squared is positive. -5 minus 3 is negative. A positive times a negative is still negative. Or we could have used our knowledge that this intercept came from a factor that has an even multiplicity. So we're going to bounce off. We're going to stay on the same side of the axis. Since we were already below here, we're going to be below here. Let's draw it. So when I'm graphing a polynomial, the only things I really end up wanting to plot are my intercepts. My y-intercept, which is 0, 0, and my x-intercepts, which is also 0, 0, and 3, 0. And then I know that my graph is negative to the left of 0, negative between 0 and 3, and positive after 3. So it's below the x-axis, it bounces off 0, and then it crosses at 3. And that's how I would like you to try graphing polynomials. Find the y-intercept, find the x-intercepts, and then for the x-intercepts, determine if you're going to get crossing or bouncing. Yeah. And do I want to say anything? Sorry, there's one other thing. Sometimes we talk about the end behavior, but I don't really. Yeah. I'm not super concerned about that. So let's do some more examples. This is kind of the name of the game. And let's look at something that's, yeah, let's look at something like that. Actually, I think I want to do one that's, sure, let's look at this one, and then we'll come back to that one. So let's try graphing f of x equal to x cubed plus x squared minus 9x minus 9. Now, I will point out that I am not a cruel person generally, and I'm not going to give you, I'm not going to make you graph a higher order polynomial that doesn't factor. Right? Thank you. Yes, I appreciate the lot. Yes, I'm not a cruel person generally. Not really, I don't think. Not on purpose, anyway. But if something doesn't factor, it's either an accident or you might not be factoring it right. So I want to graph this. I'm going to find the intercepts. So the x-intercept, sorry, I should start with the y-intercept. The y-intercept, taking x equal to 0, and f of 0 is going to be 0 plus 0 minus 9. Oh, I was cool during the trig identities. Okay, if you say so. I don't know about that. I'm just trying to help you be prepared. That's not cruelty. That's I'm kind. I'm killing you with kindness, and the kindness is I'm preparing you for your future math. X-intercepts, we're going to set this thing equal to 0. Now we need to try and factor it, and this. I only really know how to factor by grouping at this stage. So I'm going to try factoring this by grouping. So x squared times x plus 1. And then from the next two terms, I can factor out a minus 9 and look for an x plus 1. So factors as x plus 1 times x squared minus 9. And then this x squared minus 9 can factor even further. It factors as x minus 3 times x plus 3. Sorry, 1 second. Where'd you go? A little warm here. All right, cool. So my x-intercepts, right? This is one of the reasons why it's important to actually solve these factoring. So we actually want to find this. So my x-intercepts are going to be x equal to -1, x equal to positive 3, and x equal to -3. And we can see the multiplicities are all +1. You don't have to write the ones in, like I know you know there's a 1 there. This is a multiplicity of 1, a multiplicity of 1, a multiplicity of 1, which means in each of these x-intercepts, we're going to cross the x-axis. Cross. Okay. I don't particularly enjoy doing the number line thing because I feel like I'm just repeating work I'm about to do later. So here's what I like to do. I'll draw my XY coordinate system and I put the X and the Y-intercepts on there. In fact, oh yeah. So my X-intercepts are -1, 3, and -3. So -1, 3, and -3. And I know I'm going to cross each one of these. So there's really only kind of one of two things can happen. I either start down here to the left and I cross, or I start up here and I cross. So let me ask all of you, why couldn't it be this way? Well, there's a number of ways to see that. One way to see it is if it was oriented this way, your y-intercept would have to be a positive value. Exactly, good call, right? Here I'm getting a positive y-intercept, but we know the y-intercept is actually -9. So if your y-intercept is something that is not the origin, that's a really easy way to tell which way your graph should be going. So I'm like, oh yeah, I know that between -1 and +3, right, between those x-intercepts, the y-intercept is -9, meaning between here and here, the graph has to be negative. And then I'm going to cross there and be positive. I'm going to cross there and be positive, and then cross there and be negative. So it has to kind of look like that. That's really one way you can see it, is once you know what the y-intercept is, then you go up to your next x-intercept and then just kind of follow the rules, right? I go from here to here and I cross, and then cross, and I go from here to there and I cross. Now, you might be wondering, how did I know how low it went? I don't, right? We don't currently have the tools to know where exactly this turn is happening. We're not drawing a super accurate graph here. We're just drawing something that's reasonably correct. But yeah, later on in calculus, in either the 16A, 17A, or 21A, you will actually find how to find these local maxima and minima, which is kind of neat, but not the point of this class. The other thing I want to say is that you don't have to do it this way. Another way you could do it is test a point really anywhere. So you could, if you wanted to, say test a point further left than your leftmost endpoint. So for example, if I was going to test, say, x equal to -4, if I plug in -4 to the factored form, it's going to be -4 plus 1, which is negative, times -4 minus 3, which is negative, times -4 plus 3, which is negative. So when I plug in -4, it's a negative times a negative times a negative, which is negative. So I know over here at -4, the graph should have a negative y value. And then as I move from left to right, I'm going to hit this x-intercept and cross, and hit this x-intercept and cross, and hit this x-intercept and cross. I should also address, just because usually someone asks, there is no bouncing at the y-intercept, right? For a graph, the y-intercept, you're always just moving left to right. So you're always going to move through the y-axis. You're never going to like bounce off the y-axis that way. It wouldn't be a function if you did that. So there's no bouncing off the y-axis. There's only crossing the y-axis, at least when it comes to functions of x. Okay, let's look at some more examples. So x equals -4 is circled because I was talking about a different way of trying to determine the shape of the graph. And what I did was I said, I'm going to pick a point that's further left than any of my x-intercepts. So I picked kind of the easiest choice. Since x equals -3 was my leftmost x-intercept, I picked x equal to -4 to plug in. And then I plugged it in. And if you're trying to find just whether it's positive or negative, it's always going to be easiest to plug it into the factored form. Because when you multiply things together, you're just like, oh, if it's overall positive or negative, it's easy to see. Whereas if you plug it in here, you actually have to do the math. You have to negative 4 cubed plus negative 4 squared plus negative 4 minus 9 is something. So yeah, so then we determined it was negative, and then cross. They all crossed. Okay, let's look at this next one. Sure. So sometimes, because sometimes the factoring is just super complicated, sometimes I just give you their already factored form. Oh, I know what I was going to say. So let's say we were trying to graph something like f of x equal to negative x minus 1 cubed times x plus 2 squared. And I will point out another way someone might write this, which is equivalent, would be f of x equal to 1 minus x cubed times x plus 2 squared. Those are the same thing. It's just here I factored out the negative 1 cubed, which became negative 1. I want to point that out because it can be a little confusing sometimes if you see a 1 minus x instead of a, an x minus 1. Let's talk about the y-intercept. The y-intercept here, as usual, we're doing the usual, right? We're setting x equal to 0. I'm going to plug in 0. I'm going to do a little bit of work now. Let's see. So plugging in 0, f of 0 is going to be, you can use either form. I'm going to use this bottom form. It's going to be 1 minus 0 cubed times 0 plus 2 squared, which is 1 to the third. 1 to any power is 1. That's going to be 1 times 2 squared, which is 4. I will also point out, if you plug it into this one, it would be the same. You would get negative 0 minus 1 cubed times 0 plus 2 squared. And negative 1 cubed is negative 1. And then negative 1 is positive 1 times 4. So they're the same, just want to make it right. And then the x-intercept should be pretty obvious to us. So if we set this equal to 0, and I really like to kind of draw the x-intercept just right under the factors. So from the factor 1 minus x cubed, you can think of setting the entire factor equal to 0, but you really only have to set the inside part equal to 0, right? If you're setting 1 minus x cubed equal to 0, the only way something to the third power is going to be 0 is if the something is already 0. 0 to the third is the only number that you can cube and still get 0. So what I'm trying to say is you can just kind of cut out a step and say, oh, if I know 1 minus x cubed is equal to 0, I really know I'm trying to figure out 1 minus x is equal to 0. And similarly over here, I want x plus 2 equal to 0. Or I think you can also skip that step and say this one's going to give you 1 equal to x, or negative x equal to negative 1, or x equal to 1. And this one's going to give you x equal to negative 2. If you're not sure you've done it right, take that value and plug it back in. Did you get 0? If you did, then you did it right. Right? 1 minus 1, oh yeah, that's 0. Negative 2 plus 2, oh yeah, that's 0. So those are good checks to be like, if whether or not you did it right. And then for x equal to 1, the multiplicity is 3, which means we're going to cross. For x equal to negative 2, the multiplicity is 2, which means we're going to bounce. We're the bounce. I'm not really bouncing. I'm just moving up and down. Okay, so now we're going to try and draw it. And again, I'm just going to plot my intercepts. So my y-intercept is 4. My x-intercepts are positive 1 and negative 2. Okay, so now here's the thing. I know that between -2 and 1, between those two intercepts that are closest to the y-intercept, which are the only intercepts I know, between -2 and 1, I know the graph has to be positive because I have to touch that positive y-intercept. And then I know at 1, we're going to cross. So we're going to go from being positive to being negative. And at -2, we're going to bounce. So we're going to go from positive to still being positive. So now my graph doesn't look very nice, but that's the idea. So if I'm going to draw it from left to right, which is what I usually try and do, I know I'm starting over here being positive. I'm going to bounce. I'm going to hit that. And then we go through. Does this look exactly right? Definitely not. There are definitely things that are not right about the graph, and that is okay. We don't care about those things yet. So don't worry if you use a graphing utility and the actual graph looks, well, actually, let's go ahead and look, right? We might as well, right? You have these tools available to you. So if we actually graph this, and again, let me remind myself what it was, 1 y equal to 1 minus x cubed. Let me scooch this over a little bit. No, sorry, cubed times x plus 2 squared. And maybe equals, yeah, an equal sign would be good. There we go. So, right, I mean, my graph and that graph, they don't look like super different, but they don't look exactly the same, right? Notice how my graph has the peak kind of, let me stop sharing for 1 second. The graph I drew has the peak at the y-intercept kind of, or kind of right after it, whereas the actual graph has that peak way to the left of it, right? The peak is like over here. So again, you don't have to get the peak in the right place. I don't expect you to. We don't have the tools to do that yet. So don't worry about where you're deciding to turn around, is what I'm trying to say. The only time you should know where a peak or a valley is if it happens to be where your x-intercept is bouncing off the x-axis. Then you definitely have the bottom of a valley or the top of a peak. But those are the only ones you actually know. Yeah, I feel like there was something else I want to say here. So usually if I'm attempting to get it slightly more accurate, which you shouldn't worry about really, is whichever side there's more space on, like, so my y-intercept is here, and there's kind of 2 inner units worth of space to the left and 1 unit worth of space to the right. It means my peak probably is going to be on the left side. So if I was really trying to drop more accurate, I might have been like, all right, well, it's probably going to be like this, and then like, I don't know. You shouldn't worry about it. I shouldn't worry about it either. Yeah. So let's look at another example. You know, we got time. Because you're not always going to have this nice situation where you have a y-intercept that is non-zero. There are plenty of examples. I would say probably often the majority of the examples where the y-intercept actually is 0. So let's look at this next example, which is kind of partly factored for us. Let's say we've got, oh, that's terrible, James. Why would you do that? Sure. Let's say we have y equal to, that's silly, James. I should be more careful. Yeah, that's dumb. I'm just going to factor it fully. I was going to try and make it harder, but I didn't make it harder. It's already hard enough. So we have y equals x cubed times x plus 5 squared times x minus 4 to the 5th. Here's something I want to point out. I've seen a lot of people work way harder than they have to, which you know I'm totally against, right? If you take anything away from this class about me personally, you should know that I don't want any of you to work harder than you have to. You should work hard for sure, but don't do extra work if you don't need to. Oh, sorry. And someone just wrote, Someone asked what determines if it bounces across. We'll definitely talk about that again, but it's the multiplicity of the power. So we're going to see for this one, and we'll talk about it again, that the x-intercept 0 is going to cross because it has an odd multiplicity of 3. And so is the x-intercept of positive 4 because it has an odd multiplicity of 5. Whereas the x-intercept of negative 5 is going to bounce because it has an even multiplicity of 2. That's kind of the whole story about crossing versus bouncing. But we'll say it again in a minute. So if you missed it, we'll say it again. But yeah, I don't want you to do too much work. So when you're finding the y-intercept, you should be doing practically nothing here. Pun kind of intended in that the answer is literally nothing or 0, right? If I'm plugging in x equal to 0, my y-intercept is going to be 0 cubed times, I don't care. 0 times anything is 0. Negative 5, because that's an x plus 5. So you can write out the rest. 0 plus 5 squared times 0 minus 4 to the 5th. But then I see people be like, okay, negative 4 to the 5th is 1024 times 5 squared is 25, and they get some crazy 26,000. No, stop. It's 0. 0 times anything is 0. So really, I know I'm getting a little ridiculous, but I'm just trying to emphasize really, once you see you have 0 times some stuff, stop doing work. You've got 0. Okay, quick kind of aside from that. There is an exception to that statement. It has to do with limits. So when you start learning about limits later on, you might at some point have a limit that is a 0 times infinity type. 0 times infinity is not necessarily 0. So I don't want you to stress about that now, but I just want to point out that there is an exception. 0 times infinity is special. It's weird. 0 times any regular numbers is just 0. So later on, when you do this 0 times infinity, you're like, James said 0 times anything was 0. I take it back a little bit. 0 times infinity is not always 0. So yeah, but don't worry about that right now. We are not there yet. That's not until at least a quarter or two from now. So that's 0. Y-intercept is 0. Don't do too much work. The x-intercepts. So again, we're just setting y equal to 0. So we're going to get 0 equal to x cubed times x plus 5 squared times x minus 4 to the 5th. So from each of these factors, right, from the x minus 4 to the 5th factor, we're going to get x equal to positive 4 as our x-intercept. Because when you plug in 4, 4 minus 4 is 0, and y equaling 0 is where you have the x-intercepts. And from this x plus 5 squared factor, we're going to get x equal to negative 5. You don't have to jump straight to there. You are certainly welcome to write x plus 5 equals 0 and then x equals negative 5, but I think it's perfectly fine if you jump to x equal to negative 5. And then for some reason, the x by itself always seems to throw people off. When you have x by itself, you just get x equal to 0. So x to the 3rd, x to the 5th, x to the 29th power. If that's the only thing you've got on its own, that's going to give you x equal to 0 as an x-intercept. And that makes sense. If x is 4, you get 0 times some stuff, which is 0. If x is negative 5, you get 0 times some stuff, which is 0. If x is 0, you get 0 times some stuff, which is 0. And those are all the only ways that this function is equal to 0. I like to write the multiplicities, which is really just, when I say the multiplicity, I'm really just copying down the power. So the multiplicity here is 3. The multiplicity here is 2. The multiplicity here is 5. So for the multiplicity of 2, we're going to bounce because it's an even power. For the multiplicity of 3 and 5, we're going to cross because it's an odd power. Even bounce, odd cross. I feel like the bouncing, like the B bouncing kind of makes sense because like the B, if you draw the B like this, the B kind of bounces off the axis. That's kind of, I like that. I mean, it's not like the best thing I've ever thought of, but it kind of works. I don't have anything for cross, sorry. And I'm kind of out of room to draw this, so let's draw it on the other side. We'll come back to it. So let's see here. So yeah, we're doing that. We have y equal to x cubed times x plus 5 squared times x minus 4 to the 5th. And let's see, we have x equal to 0. This actually said we have y equal to 0. We also have x equal to 0. And then we have x equal to positive 4 and negative 5. So what I want to mention here is that the y-intercept being 0 doesn't tell us anything about if the graph is above or below the x-axis. So typically what we need to do here is find one more test point. You can pick anything you want. You could pick, say, 1 if you wanted to. And say, okay, if x is 1, then I don't care what value y has, I just care if it's positive or negative. So if x were to be 1, for example, y is going to be 1 cubed, so a positive number, times 1 plus 6 squared, so another positive number, times 1 minus 4 to the 5th, which is a negative number to an odd power, which means it stays negative. So we have a positive times a positive times a negative, which means y is negative when x is equal to 1. In fact, the odd even power thing, bouncing or crossing, is totally because if you have something to an even power, it's never going to change signs, right? Something squared, whether it's a negative thing squared or a positive thing squared, it's always going to end up being positive. So when you cross from one side of a thing to an even power to the other side, you don't change signs because this factor doesn't change. Whereas when you have, say, something to an odd power, if the insides are negative, it's negative overall. But if the insides are positive, a positive thing to the 5th power is positive overall. So that's what's happening here. So I know when x is 1, I'm going to be negative. And then at 4, I'm going to cross like that. At 0, we're also crossing because 0 came from x cubed. And then at negative 5, we are going to bounce because of the even multiplicity. Yeah, so just to point out, if you pick something like negative 6 cubed is negative, negative 6 plus 5 squared is positive, and negative 6 minus 4 is negative, 2 not power is negative. So when x is 6, I have a point here. Bear with me just 1 second. When x is negative 6, you have a negative times a positive, but really it's a negative number squared times a negative, because a negative number to an odd power is negative. But then when you pick something between, say, negative 5 and 0, so like when x is, sorry, I'm running out of room here. When x is negative 3 cubed is still negative. It's a negative, it's a negative, it's a negative. Negative 3 plus 5 changed signs, right? It was a negative thing, right? It was negative 6 plus 5, which is negative. Now it's negative 3 plus 5, which is a positive. But the positive thing squared still doesn't change, right? This negative squared versus this positive squared is the only difference. And since they're both being squared, that's why we're still above on either side of negative 5 because of that even power there. Hopefully that makes some sense. I'm just trying to point out that when your power is even, you're bouncing off because literally the sign isn't changing at all. One other graphical thing about this. I have not drawn this very accurately. And there is one thing we can do to make our graphs a little bit more accurate without kind of involving more work. Specifically, when your intercepts have a multiplicity that is 3 or higher. So if your multiplicity is greater than or equal to 3, you typically have something a little screwier at your x-intercept. So you kind of get a flattening out behavior, meaning at both of these actually, at x equal to 0 and x equal to 4, right, where the multiplicity is 3 and 5 respectively, it kind of looks more like this. It kind of flattens out weirdly, and I didn't drop very well at all. Let me try that again. So right here at 0, it kind of does this weird like flattening out and crossing strangely like that. And the same thing's gonna happen over here. You don't have to do this, but I just want you to know that when you have multiplicities that are 3 or higher, you do get kind of a funky looking shape. And you can totally see that if you graph it in something like this, which again, I would encourage all of you to do if you want to. So if x plus negative, I'm not sure what if x is -3. So let's add, yeah, so if x is -3, the overall y value is positive. And we can see that from the graph, right? When x is -1, 2, 3, right, the corresponding y value is definitely a positive value. When x is -6, the corresponding y value is definitely a positive value. When x is +2, the corresponding y value is definitely negative. And when x is bigger than 4, like say +5, the corresponding y value is positive. So if we were to draw the sign chart for this, not that we need to because we have the graph, but you could totally draw the sign chart from the graph. Right, we can see that over here, the graph is positive. Over here, the graph is negative. Over here, the graph is positive. Over here, the graph is positive. Yeah, you can say that. The y value will determine the direction in which the cross goes. Sure. But the thing is, basically, what I'm trying to kind of say here is you need to know a y value, right? And before I picked x equal to 1 or x equal to -6, I didn't have any y values. So I didn't know anywhere where it was either above or below. But once I know one y value, and you really only need one y value, specifically the y-intercept, if that happens to be not 0. I should say you need one y value that isn't equal to 0. So the y-intercept here is not helpful because it is 0. But if I know one other y value, really not even the actual number, just whether it's positive or negative. Oh, it's 223. I went too far. So sorry. So knowing when you plug in -6 that it's a negative times a positive times a negative, which is positive overall, then I know the whole shape of the graph. Because I know it's positive here. It's got to bounce at -5. It's got to cross at 0. And it's got to cross at 4. That's what I'm really doing.